The Troll. A gas platform is the largest structure ever transported by man across the Earth's surface, and is the second heaviest object ever moved by humanity, weighing an incredible 1.2 million tons. This enormous structure, a true feat of engineering, was designed and built to extract natural gas from the depths of the Troll gas field, and posed major challenges that its designers had to overcome. How will a 1.2 million ton structure be transported? How will a huge structure be anchored in the sea? How can we ensure that during a major storm with strong winds and waves up to 30 meters high, the platform won't fall or have its structural integrity compromised? How would the platform behave during a major earthquake? Most importantly, how will the gas extracted here be transported to Norway? These were some of the problems that the engineers needed to solve to make this incredible structure possible. But before we get to the video, I want to say that you can already become a supporter of the channel by subscribing to any of the 3 available packages. There aren't any major benefits yet, and you can also stop supporting the channel at any time. Subscribe. The construction of Troll A has its origins in 1979 with the discovery of the Troll gas fields off the west coast of Norway in the North Sea, which were estimated to hold 1.8 trillion cubic meters of natural gas and 2 billion barrels of oil. With this monstrous amount of natural gas, an equally monstrous platform was needed to extract it. And so, in September 1999, construction began on the enormous gas platform. But the legs of the platform were among the most critical and important points and needed special attention. The 303-meter high legs needed not only to be tall, but also extremely strong, resistant, flexible, and above all, waterproof. In other words, to keep water out. Concrete was the most promising material to meet these requirements. Concrete is currently the most widely used man-made material worldwide. But concrete has a fatal flaw. Let's go back to the 19th century. The architect Charles Hagelin noticed that when something was built in parts, it was very difficult to make it waterproof in the area of the joints. Furthermore, the areas where concrete elements meet at different times are weakly bonded. And, to make matters worse, if we have a large cement structure built in parts, this means that instead of the structure resisting the loads applied to it, as a single piece it will resist by behaving like several independent pieces but joined together. This makes it unstable, dangerous, and potentially prone to collapse. This means that the gigantic 303-meter tall legs, conical in shape, ultra-resistant and waterproof, cannot be made in parts, but must be built all at once without pauses, without interruptions, and without joints as a single piece. But how do you make a structure of these proportions as a single piece? Charles Hagelin faced the same problem in the 19th century, but the solution he found was quite simple. The solution to making huge, seamless structures is to pour the concrete continuously, without pauses or interruptions, from the beginning to the completion of the structure. The system responsible for accomplishing this is known as slipform, which allows for continuous, precise, and rapid vertical construction of reinforced concrete structures in a wide variety of shapes and sizes. A form with the shape of the intended structure is assembled around the steel reinforcements, and then the concrete is poured. Then the hydraulic system raises the entire platform a few centimeters upward, and the concrete is poured again, and so on. The system never stops, and the structure never stops growing without interruptions and without joints. That's why when we look at the pillars of large structures, they not only appear to be, but actually are a single piece without seams and without weak points, making the structure much safer and stronger. But even with the use of ultra-fast sliding forms, given the size of the platform legs, the structure took almost a year to be completed. The Troll. A platform was built to withstand the enormous stresses generated by the winds of the most intense storms, and to withstand waves up to 30 meters high. and the platform is expected to last until 2066. With its 472 meters in height, from the base to the top of the gas platform, Troll A still faces hidden danger within its own structure. The long legs, just over 300 meters, hide a potential problem that could cause this structure to collapse. Something as simple as a musical note could send this structure to the bottom of the sea. Let's go back to November 7, 1940. The Tacoma Bridge, located in the Tacoma Narrows in Washington, United States. With just over 1,800 meters in length, 12 meters in width, 135 meters in height, and steel cables 43 centimeters in diameter used to support the deck, this bridge was designed to be a revolutionary structure. The inauguration took place on July 1, 1940. It was the third largest suspension bridge in the world, with a central span of 853 meters. Soon, locals noticed a problem with the bridge. Even moderate winds made it sway a lot, and it was already common to see cars disappearing from view when the bridge went up and down. However, 4 months after its inauguration, the revolutionary steel and concrete bridge began to twist violently. One of the bridge's designers checked to ensure it was still safe, even as the edges rise and fall by up to 8 meters. However, the twisting intensified, and the bridge held out for several hours until the structure collapsed. A structure collapsing, even without casualties, is a structural engineer's worst nightmare. The problem was caused by a phenomenon called flutter, also known as aeroelastic resonance, which is an aerodynamically induced condition of self-excitation or negative damping in the torsional degree of freedom. It works as follows. It is known that any structure or object has a specific frequency at which it vibrates. This frequency depends on the material, the mass, and the stiffness of the structure. When we strike a glass, at the same time it emits sound. It also vibrates. And the frequency of these vibrations per second is its fatal flaw. This means the process can be reversed. Instead of causing the vibrations by hitting the glass, you can cause the same vibrations in the air by playing a sound at the same frequency as the glass, making it vibrate until it breaks. This is called resonance. The huge legs of Troll A resemble guitar strings, each vibrating at a specific frequency. This means that the ocean waves can hit the legs in a rhythm and in a sequence that makes them vibrate continuously until they can't take it anymore and collapse. Fortunately, the engineers knew how to solve it. The solution is a huge concrete block called a shortener that connects the 4 legs of the platform, designed to eliminate possible resonances caused by the ocean waves. Thus, the concrete block raises the specific resonance frequency of the structure to a much higher level where the ocean waves can't cause vibration or collapse. With the problem of the legs solved, it was time to move on to the next challenge. The Troll, a platform currently operated by the company Equinor, was built 300 kilometers away from its current location. The legs and the platform itself were built separately and needed to be joined together. For this, the 300-meter hollow legs were filled with water, becoming almost completely submerged. This was the most critical part of the entire construction process, with the meter-thick legs having to withstand water pressure of 380 tons per square meter. The engineers had a terrible memory from 5 years earlier, when, due to a design error, another platform, Sleipner A, when subjected to similar controlled submersion conditions, collapsed, causing an earthquake that reached 3 on the Richter scale. But the legs of Troll A stood firm against the water pressure. Now it was time to position the platform over the legs, raising the legs centimeter by centimeter until they were at a final distance of just 1 meter. A day later, the enormous 656,000-ton structure was a single piece. Now the platform needed to be lifted to be transported to its final destination, crossing the fjord strait to its destination in the Gastrol gas fields. Ballast tanks were added to the structure, and 10 tugboats handled the entire 200-kilometer transport journey over the course of a week. It was the tallest structure ever transported by humans, moving an incredible 1.2 million tons, including the ballast tanks. Now, you must be wondering how it's possible for a 1.2 million ton structure to have been almost completely sunk, then resurfaced, and now be floating on the water? If you remember the video where I talk about how submarines dive and surface, the principle is exactly the same. It's simply a matter of balancing and unbalancing forces. Transportation resolved, it was time to face the next challenge. The Troll. A gas platform alone weighs 683,600 tons. Even with the weight of the ballast tanks, which brings the total weight to 1.2 million tons, it still wasn't enough to anchor the $650 million platform firmly to the seabed. Some solution was necessary. The engineers then looked to the past for inspiration. Let's go back to 1654. Physicist Otto von Guericke conducted a public experiment to show the power of the vacuum. He sucked the air from a sphere for that. The absence of air and the creation of a partial vacuum generated a tremendous force that kept the two halves of the sphere together. Not even the 16 horses that were part of the experiment managed to separate the two halves of the sphere. Based on the principle of vacuum generation, the engineers at Troll A adapted Guericke's idea for a set of 19 suction piles at the base of the platform, with each of these piles being 40 meters tall. Upon reaching the final destination, the legs of the platform were flooded again so that the platform would sink. Once it was sunk, a vacuum was created in the 19 suction piles, causing 36 out of the 40 meters of the piles to go into the seabed, thus anchoring the platform. Now, not even 30-meter waves or strong winds could knock the platform over. But the final and possibly most important challenge remained: justifying Troll A's existence. How to send the gas from here all the way to Norway. The Troll. A platform began its production in 1996, and in total, the platform extracts natural gas from 40 wells, which are later transported through 70 kilometers of pipelines to Norway. Early in the explorations, the well's internal pressure was so high that gas could be transported to Norway with minimal machinery. However, 10 years later, the engineers noticed that the internal pressure of the wells was decreasing, and now it was necessary to use some method to suck the gas from the wells and blow it to the continent, maintaining production levels according to the company's interests. And so compressors were used, which are equipment based on the operating principle of a vacuum cleaner fan or even an airplane engine. It sucks on one side and blows on the other. However, Troll's compressors do this on a much larger scale. Troll's compressors take the gas from the wells and blow it for 70 kilometers to Norway in just 84 seconds, which means a speed of 3,000 kilometers per hour or 833.3 meters per second for 80 million users in Europe.